In this video, we're going to talk about some applications of using logarithms to solve exponential equations. So remember back in the exponential functions unit, we talked about growth and decay equations. And remember we said we can use growth and decay equations to model several different real-life situations. So we're actually going to use all of those same equations in this lesson, but we're going to be solving for a different variable. Now that we know about logarithms, we can actually solve these equations to find a missing value in the exponent, which is different than what we were doing in the previous unit. So let's look at this example. It says the population of a town is 5,000 in the year 2010. Its population increases by 12% each year. After how many years will the town have 10,000 residents? The key here is that it says increases and it gives us a percentage. Remember when we have this kind of situation, we use this formula right here, this y equals a times 1 plus or minus r to the t, right? We're going to use this formula. Let's go ahead and identify our variables. So our starting value is a, so a is equal to 5,000. Our rate of change is 12%, which we can convert to a decimal by moving it two places to the left. That's 0.12. And then the final value is going to be y equals 10,000 residents. Okay. So now it says after how many years? Okay. So after how many years means t is our unknown value. So let's go ahead and plug this all into the equation we have. So we have 10,000 equals 5,000 times 1, and then we're going to do plus 0.12 because notice here it's increasing, so 1 plus 0.12 to the t. So we have 10,000 equals 5,000 times 1.12 to the t. Okay, so now we need to isolate that exponential term. So in order to isolate the exponential term, we're going to go ahead and divide both sides by 5,000. So when we do that, we get 2 equals 1.12 to the t. Okay, so now let's go ahead and take the log of both sides. So we do the log of 2 equals the log of 1.12 to the t. Okay, so now to solve this, we're going to use that power property and go ahead and bring that t down in front. So we have the log of 2 is equal to t times the log of 1.12. Okay, so now we need to solve for t. We can solve for t by going ahead and dividing both sides by the log of 1.12. Right, so I'm going to divide both sides by the log of 1.12. So here this is going to cancel. That's going to tell me now that t is approximately equal to, I'm going to go to my calculator and I'm going to do the log of 2 divided by the log of 1.12. You can see here that gives me a decimal. I'm going to round it to the nearest tenth, so that is about 6.1. And so that's 6.1 years, okay? And if I think about this, that actually makes sense, right? So if it's increasing at a rate of 12%, it does make sense that after 2010, it's going to take about 6.1 years to get up to 10,000 residents. Okay. So whenever you solve these problems, you want to take a minute and think about whether the answer you have actually makes sense in the context of the problem. So now you can go ahead and pause the video and try doing this example on your own. So here we have petri dish with bacteria that is doubling. So we want to use the growth and decay equation y equals ab to the x. A is going to be the starting value 200. Doubling means that b is 2 and then y is going to be 6,000. So that gives us the equation 6,000 equals 200 times 2 to the x. We go ahead and divide both sides by 200 and that gives us 30 equals 2 to the x. Take the log of both sides. We have log of 30 equals log of 2 to the x, and then we bring the x down in front. And then we go ahead and divide both sides by the log of 2. Log of 30 divided by log of 2 gives us approximately 4.9 hours, right? And so that makes sense. If it's doubling every hour, it's probably going to take about 4.9 hours to get from 200 to 6,000. So now let's try this example. It says Susan invests $8,000 in an account that earns 5% annual interest compounded quarterly. How many years will it take for the balance of the account to reach 10,000? So since it's compound interest and we have a compounding schedule, we're going to use this formula right here. Remember that A is equal to the starting value, so 8,000. R is equal to the percent, so that's going to be that 5%, which we can go ahead and convert to a decimal, moving it two places to the left, so that's going to be 0.05. N is equal to 4 because that's our compounding schedule, right? Quarterly means that compounded 4 times. T, we don't know, right? It says how many years, so T's are unknown. And then $10,000 is going to be the final value in the account, right? So 10,000 is where the account ends up. So if we plug everything in, we have 10,000 equals 8,000 times 1 plus 0.05 divided by 4. And that's going to be to the 4 times t power. Okay, so let's work on simplifying this. We have 10,000 equals 8,000. And then what I like to do is simplify that everything I have in parentheses. So I'm just going to go ahead and do like 1 plus 0.05 over 4. And you see that's 1.0125. So I'm going to put 1.0125, and that's to the 4t. I still need to isolate that exponential term. It has that 8,000 in front. So I'm going to divide both sides by 8,000. So when I divide both sides by 8,000, I have 10,000 over 8,000. So I'm going to just go ahead and divide on my calculator. 10,000 over 8,000. That gives me 1.25. Okay, so I have 1.25 equals, and then here this cancels, and then I have 1.0125 to the 4t. Now I can go ahead and take the log of both sides. So I have the log of 1.25 equals the log of 1.0125 to the 4t. I'm going to go ahead and bring that 4t down in front. So I have the log of 1.25 equals 4t times the log of 1.0125. Okay, so now remember I need to divide by everything but the variable, right? So I'm going to divide by 4. I'm going to divide by log of 1.0125. And whatever I do on the right side, I have to do on the left. So I have 4 log 1.0125. Here, everything cancels, leaving me with just t. So that means t is approximately equal to, let's go to our calculator now. So I'm going to clear some of this, and we're going to do log of 1.25 divided by 4 log 1.0125. Okay, and so you can see that is a decimal, which we can round now to the nearest tenth. That means t is approximately equal to 4.5 years. Okay, and that's a reasonable value for the amount of time, right? It makes sense that after about 4.5 years, this is going to go from 8,000 to 10,000 if it's a 5% interest rate compounded quarterly. Um, Now you can go ahead and pause the video and try doing this example on your own. So here we have a car depreciating at a rate of 30%. So the starting value is going to be 16,000 and the final value is 7,000. Remember, we're going to use this decay formula, y equals a times 1 minus r to the t. R is 30%, so when we do 1 minus r, that's going to be 0.70. We go ahead and divide both sides by 16,000 to get that exponential term alone. And then we go ahead and take the log of both sides. So we have the log of 0.4375 equals the log of zero point 0.7 to the t. Remember, the power property allows me to bring that t in front, and then I divide both sides by the log of zero point 0.7, which gives me about 2.3 years. Okay, that is a reasonable value. That makes sense. That it would depreciate from 16,000 to 7,000 in about 2.3 years if the rate is 30%. So exponential equations can be used to model many real-life situations. If there's an unknown value in the exponent, you can use logarithms to determine the missing value.